Namaste and warm welcome to all of you for yet another lecture on the mathematical foundations of machine learning. In the last couple of classes we have been looking at the idea of linear transformations. What is a linear transformation, what does it do, why is the study of linear transformation important, and then we looked at it from the idea of reshaping the vector space and so on. So, let us try to spend some more time on this before we get on to the idea of eigenvectors and eigenvalues. So, in this case in this class what we are going to do is we are going to spend some more time on linear transformations, maybe study a couple of linear transformations here, and then we go on with our eigenvalues and eigenvectors, right. So, let us get on with the idea of linear transformations. So, recall the definition of linear transformations. Let us just do a quick recall. Say that a linear transformation you can also call it as a linear map or a linear map. T, the transformation is denoted by T from, let us say, a vector space say V to another vector space W. We will not say another vector space, we just say to a vector space because it could actually map to V itself, to a vector space W. Is basically a map that satisfies the following properties. So, what are the properties? We have number 1, the transformation of the 0 vector in V takes you to the 0 vector in W, right. The 0 vector in V is always mapped to the 0 vector in W. Then we know that the transformation of, let us say, U plus V, 2 vectors, is nothing but the sum of transformations. This is nothing but T of U plus T of V, let us say for U and V in the vector space V, right. And the third one, transformation of this vector, let us say alpha U, is basically given by alpha times the transformation of U for U in the vector space V, right. These two are vectors and that big V is basically the vector space, right. So, let us have that in mind. So, what is it to say? Well, first most important thing is that a linear transformation or a linear map, it always maps the 0 vector in one vector space to the 0 vector in the other space. This is very essential, only then you call that as the linear transformation. Now, let us take some, we have already seen some examples. Let us look at, in fact in the last couple of classes we also looked at capturing the linear transformation in terms of matrices, right. Suppose I want to say what does this transformation do, I want to capture the transformation, I could capture the transformation in terms of a matrix and say that look, okay, the matrix is going to transform these vectors, the transformation represented in the form of this matrix is going to transform this vector to some other vector, right, that is what we have seen. So, let us spend some time, a couple of minutes on that, and then let us go ahead. Yeah. So, matrix representation of transformations. Oh, in fact, just before that we will just make this statement, this is very important. A very important note that we want to do. We say that a linear map or a linear transformation a linear map T. Say for example, I have I have let us say this line passing through the origin, right. I have a line passing through the origin, let us say this L1, and I am going to apply this transformation T on the set of vectors along this line. You already know what it is, it is basically a one dimensional vector space. So, what we want to do is let me see if I can actually if I apply this map onto the line passing through the origin, I end up getting another line passing through the origin. It is basically yet another line passing through the origin in the vector space. So, we will say that every linear map basically maps line passing through the origin to another line passing through the origin, a plane passing through the origin to a plane passing through the origin. So, this basically maps, we are going to say this. So, T of L1 is basically some other line, let us say L1 dash. This is a very important understanding that we have. So, lines maps linear map T always sends or maps lines passing through the origin to lines passing through origin, right, to lines passing through the origin. Right, we have a linear map which says it always maps or it always sends lines passing through the origin to lines passing through origin in the other what you call in the other space. So, this is what we have, but let us take a simple example here to see whether the statement is correct. Let us look at this. Let us take a simple example. Let us have this transformation, let T be represented by this transformation, be represented we will say T be a linear transformation represented by the matrix, a linear transformation let us say represented by the matrix A where A is given by let us say 2 1 and let us say again 2 1. This is what the transformation is that in the matrix form. Let us look at this. So, what it does, let us take this. So, I want to look at what happens to the set of vectors x y in R2. So, I am going to look at let x be a vector in R2, let x be in R2. Now, what I am going to do is I am going to look at what it does 2 1 2 1 into x y. Now, this is like I am going to have 2 x plus y and 2x plus y, right. It is going to be 2x plus y, 2x plus y, that means both the components are like this 2x plus y and 2x plus y. So, what I am going to do is I am just going to look at a set of vectors and see what this transformation does to a set of this set of vectors. Let us look at this 2 1 2 1. Let me look at this. You know that if it is a linear map, this fellow is going to map the 0 vector to the 0 vector. So, the 0 vector gets mapped to the 0 vector. Let us look at this 2 1 2 1. I am going to look at this. So, what is that 1 minus 2. I am going to look at what it does to this vector 1 minus 2. We already know this is going to be of the form 2x plus y. So, I am going to have this is going to be 2 plus minus 2 and I am going to have 2 plus minus 2, which is basically 0 0. Let us look at this vector 2 1 2 1. The action of this transformation or this transformation on the vector, let us say minus 1 2. This is going to be again minus 2 plus 2 minus 2 plus 2. Oh, something interesting happens here. What is that? Now, if you look at the set of all these points, suppose I take this 2 1 2 1. Why just put 1 minus 2 and minus 1 2? Instead, let us take k minus 2k, right. If you take any k to minus 2k, this is going to be 2k minus 2k and that is going to be 2k minus 2k and I am going to get 0 0, right. I am going to get 0 0. Now, what is interesting here? What is the geometry of this set of points k minus 2k? I want to look at the geometry of this set of points, right. This is going to be the scalar multiple of this vector 1 minus 2, which means this is going to be, if we will just plot, let us plot and see what happens. So, I am going to have this. So, let me mark these axes, let us say x1 and x2 and I have 0 1 2 3 4 5 minus 1 minus 2 minus 3 1 2 3 and 4 minus 1 minus 2. Now, let me look at the geometry here. So, 0 0 is here, then we had 1 minus 2, we are talking about multiples of 1 minus 2. So, 1 minus 2 is basically this point, minus 1 2 is going to be here. So, this is basically a line passing through the origin, right. This is basically a line passing through the origin and let us assume that this is the domain of the transformation T, domain of transformation T represented by the matrix A. A is equal to 2 1 2 1. This is the domain of the matrix A represented by which is this domain. This is basically this entire what do you call this this R2 is basically the domain. Now, what I am going to do is I want to just see what is happening to the set of points along this line, which is basically L defined by k into the set of points k into 1 minus 2. Now, what did this map do? This map 2 1 2 1 basically took this is let us say A representing the transformation T. This took the entire set of vectors along that line and it put somewhere. Where did it put? So, basically we had this, right. You had this is 0 1 2 3 4 1 2 3 minus 1 minus 2 and then a minus 1. This is the say x1 axis and that is the x2 axis. Now, where did this line in entirety get mapped to? That is the most important and interesting stuff. So, the line in its entirety got mapped to the 0 vector. So, we say this 2 1 2 1, the transformation was basically taking any k minus 2 k to the vector 0 0, right. It is taking a vector to 0 0. That means it is not just that any line passing through the origin gets mapped to another line passing through the origin, it could also get mapped to the origin itself. So, let us write this. We will have to make a small modification to what we have written in the previous slide. We say that look, a linear map T always sends map or maps lines passing through the origin to lines passing through the origin, not just that, or onto the origin itself, or onto the origin itself. That is the beauty here. Right, that is what we have here. So, a linear transformation, you have a line here passing through the origin, when it maps it is going to map it to another line passing through the origin, or it is going to put it to, I mean it is going to map it onto the 0 vector there, the 0 vector in the other space, right. So, that is pretty interesting here. So, if you have a plane passing through the origin, who knows, that entire plane could be mapped to the 0 vector. I mean if you remember, I mean we have talked about subspaces. I will come to the subspaces associated with linear transformations and subspaces associated with the matrix in some time. You will be able to see that if you have a line which is passing through the origin that gets mapped to the 0 vector by the matrix, or the matrix representing a transformation, we call such set of vectors which get mapped to the 0 vector, we call that as the null space of the matrix A. And with respect to the transformation, this was called the null space of the transformation. It was also called as the kernel of the map or the kernel of the transformation, right. So, that is what we have. Let us look at further, right. So, what are we going to do now? Let us take, let us get to the, suppose I tell you that this is the transformation, how do I get the matrix representing the transformation? So, that is what we are going to do now. So, what are we going to do? Given a transformation, how do we get the matrix representation of the transformation? Right. How do we get the matrix representation of the transformation? This is a question that we want to answer, but before that we will also recall another interesting property or of the linear transformation. We will just make a note of that before we get into answering this question. What is that? Suppose T is a linear map, let T be a linear transformation from, let us say, some vector space V to W, right. You remember this vector space, I have, let us say, the vector space V and I have another vector space W here. So, what is T going to do? It is going to map the 0 vector here, it is going to map to the 0 vector there. It is going to map any other vector that we have here, it is going to map it to some other vector over there. So, the map basically takes this, T of 0 is equal to 0, we are going to say T of V in V is going to be, say, some vector W in W. This is what we want. Now, what I am going to ask is, given that you have a vector space and the vector space has infinitely many vectors, how do I study, or what is the effect of this transformation, linear transformation T, on the entire vector space? This is something which we wanted to look at, and in the last class we made a mention that look, if you want to find out what is the effect of a transformation in the vector space V, do not do the transformation on each and every vector there in the space V, because you are going to have infinitely many vectors. Instead, what you do is you find out what it does to the basis for the vector space. if you know that, by the very property of linear transformation you know what happens to every vector in the vector space V, because you are going to have every vector to have a basis representation, and basis representation of a vector in a vector space is unique. So, that is the most important stuff. So, what we are going to do is we are going to make a very important and very profound or strong statement here. We are going to say any linear transformation T mapping from, let us say, V to W, any linear transformation T such that it maps vectors in V to W is completely determined by what it does to the basis vectors of V. What does that mean? It simply means the following. So, any linear transformation T mapping from, let us say, V to W is completely determined by its action on a given basis or on a basis of V. That is the most important stuff. Let us say, let us just take a generic case, let us prove this a bit, because it does not require a lot of time to prove this, just let us just try to prove it. So, let us take, if let us just do this, let V and W be two vector spaces such that a linear transformation T maps vectors from V to W, right, and let us have this, let V1, V2, let us say Vk be a basis for V. So, and then let us say let W1, W2 etc., let us say Wn, we do not say W1, W2, Wn, let us say let Wi for I is equal to 1 to n be any set of vectors in W. Now, what we say is, okay, we can actually say this. So, let us take up this. We will say this, then there exists or there is a unique map What kind of a map it is? It is a linear map. So, there is a unique linear map T from V to W such that the transformation of, let us say, the vector Vi is going to be the Wi vector. Is this clear? So, what are we going to do? So, we are just going to look at the proof for this. It is a very small proof, a very interesting one. So, suppose we, so what we are going to do is we are going to take the proof for this. So, what we will do is we will just consider a general vector V, let V be a vector in V. Therefore, V has a, okay, therefore, this small vector V has a basis expansion in V. Basis expansion in the big V. This is what we have, and what is the basis expansion? We know that V is going to be a linear combination of the basis vectors in V. So, let me say alpha 1 V1 plus alpha 2 V2 plus etc. plus alpha k Vk, where alpha i's are some scalars, right. So, alpha i's are scalars. Now, what we are going to do, I am going to say that look, we already have the map which is there. What is the map? We have this, the transformation which is going to map a vector in V to a vector in W. Therefore, what I am going to say is the transformation of this vector V is going to result in, let us say, some other, this is going to result in a this is going to result in a vector in W. So, let me say alpha I Wi, right. So, what we are going to do is we are going to say that okay, let us do this. So, Vi is equal to, what is Vi? The ith vector, this is going to be in terms of basis expansion. I am going to have 0 V1 plus 0 V2 plus etc. plus 1 time Vi plus 0 Vi plus 1 plus etc. plus 0 Vn. This is what we have, right. Now, what is the linear transformation of Vi? Linear transformation of Vi is going to be, this we already know, the definition of linear transformation says that from the definition of linear transformation we have T of alpha u plus beta V is nothing but alpha transformation of u plus beta transformation of V. So, this is what it is. So, the in this case what happens, this is going to be 0 times the transformation on V1 plus 0 times the transformation on V2 plus etc. plus 1 time transformation on Vi plus every other term is going to be 0. Which means transformation of Vi is going to be this vector, okay, this vector, let us do this Wi, right. Why do we say that? We say that, okay, you are going to say this transformation of, where does this transformation of V1 going to take me? Transformation of V1 is going to take me to W1. So, it is going to be 0 times W1. So, what we essentially see is we are going to say that transformation of Vi is going to be the vector Wi. So, what do we want to prove? We want to prove that T is a linear map. So, what we are going to do is this. So, what is the claim we have? We claim is basically T is a linear map. In fact, if you look at this, we are just going to define this map T. Let us not take that to be a linear map, then only this works. So, because we are claiming it to be a linear map. So, what we do is we say that we are going to define a map which is going to take some vector V in V to a vector W in W. So, we are going to take that to be a map, but the claim is going to be that it is a linear map, right. So, let us look at this quickly. So, what are we going to do? We are going to say that we are going to take two vectors, let u comma v be two vectors in V, and therefore u has a linear expansion in terms of basis. Let me call this as, let us say, I is equal to 1 to k. So, in fact I have used k here. So, let me actually make this as k. We have taken it as Vk. So, this is going to be k. So, this is going to be 0 times t of Vk. So, this is what we have. This is also going to be Vk. We have taken k vectors here. We will use the same stuff here. So, I have say, let us say this is going to be alpha I Vi, and let the vector V be equal to sigma I is equal to 1 to n or 1 to k beta I Vi. Right, this is what we are going to have. So, what is u plus v? U plus v is nothing but sigma alpha I Vi, I is equal to 1 to k plus sigma beta I Vi, I is equal to 1 to k, which implies I am going to get this as, because both of them are like vectors Vi. So, I am going to write this as alpha I plus beta I into Vi, I is equal to 1 to k. Now, I am going to look at transformation of this. So, I am going to do this transformation of u plus v, t of u plus v. What is t of u plus v? This is nothing but transformation of this entire thing that we have, this with the vector that I get as alpha I plus beta I into Vi, I is equal to 1 to k alpha I plus beta I into Vi. This is what we have, right. So, this is nothing but, what is the transformation? We already saw that transformation of ui is going to be, transformation of V1 is going to go in the direction of V1, transformation of V2 is going to be in the direction of W2. So, T of V1 is W1, T of V2 is W2, and so on. So, what I am going to have, this is going to be sigma alpha I plus beta I into Wi, I is equal to 1 to k, right, which is the same as sigma alpha I Wi plus sigma beta I Wi, of course I is equal to 1 to k, I is equal to 1 to k. This is what we have. Now, what is that? This is nothing but transformation of the u vector plus the transformation of the v vector, right. This is what we have. Let us take one more, that means you have proved the linearity here. T of u v is nothing but T of u plus T of v. Now, what we are going to do is we are going to take the next one, we are going to look at the scalars, a scalar multiplication of the transformation. So, what I am going to do is let C be a scalar, a real scalar, then we are going to look at C times a vector v, which is nothing but C times the linear combination of the basis vectors for v, I is equal to 1 to k, what we have, alpha I Vi, this is what we have, right, which is nothing but I is equal to 1 to k C times alpha I into Vi, right, C times alpha I into Vi, which means the transformation on Cv, when you apply the transformation T on Cv, what are we going to get? We are going to get, this is going to be C times alpha I, let us say, into Wi, I is equal to 1 to k, and that simply means it is going to be C times, C is common everywhere. So, I will pull that out, I am going to have C times I is equal to 1 to k alpha I Wi, which is nothing but alpha times transformation or C times transformation of V, C times transformation of this vector V, because this is going to be the transformation that I am going to get. This is a basis expansion, this is going to be the transformation of V. So, I am going to get transformation on Cv is nothing but C times transformation of V, and now we see that T is a linear map. So, we see that therefore, T is a linear map. Right. I mean, you can also prove the uniqueness. I will just leave that as exercise to you. You can prove uniqueness of the transformation of the linear map. You can prove it. Now, how do we prove it? It's not a difficult one. So, what you do is you take another transformation, let us say T dash, which is going to map the vector from W, I mean the V to W, such that your transformation of Vi is going to give you Wi. Now, all you need to prove is you look at the basis expansion, and then you need to prove that this is going to be unique. So, that can be done. So, I leave that as an exercise to the readers. Now, we are still left with a question. What is that question? How do we get the matrix representation of the transformation? So, the question still remains. Question is, how do we get the matrix representation of a transformation? Right. Let us look at this. How do we get the matrix representation? Right. This is a question that we have. So, how do we get to the matrix representation of the transformation? We will just take a simple example. So, consider this example. Let V be a vector space. Let us say let V be equal to R2, right, and let W be the following vector space, the subspace first of all let us forget about the subspace. Let us take W be also R2, W also be R2. Right, we are going to take W also to be R2. Now, what I am going to do is this let us consider this transformation. Let T be a transformation such that it takes any vector. So, the action of Ty is the such that. So, let us do that. So, T, okay, let me make this, let T be a linear transformation such that T is such that it sends every vector x comma y to, let us say, let us say x plus y, and let us say x minus y, right. So, what it does is the transformation T takes two vectors, I mean T takes a vector in R2, let us say x comma y, and then what it says is it is going to map every vector x comma y to basically a vector whose components are the sum of the two, the first component being the sum of the two components and second component being the first component minus the second component. So, obtain the matrix associated with the transformation. Obtain the matrix associated with this transformation. Now, that is the goal, that is the question that we are trying to answer. How do we get the matrix associated with this transformation? So, what we will do is we will look at the answer to this in a quick way, and then we will dwell upon this in the next lecture. So, what we want to do is, you know that any vector in R2, let us say x be a vector in R2, can be expressed as the linear combination of the standard basis x into 1 0 plus y into 0 1. This is what we have. So, therefore, the transformation on xy, I can write this as, since T is a linear transformation, I am going to write this as T of x into 1 0 plus y into 0 1, and we know what is this? This is going to be, since it is a linear transformation, I am going to write this as x into the transformation that it does to the vector, let us say 1 0. So, x times transformation of the vector 1 0 plus y times the transformation of the vector 0 1, right. Now, all I want to do is I want to figure out what the transformation does to 1 0 and what the transformation does to 0 1. What does it do to 1 0? 1 0 is basically the transformation says, look, I am going to have, so T maps x y to x plus y, x minus y. So, T of 1 0 is nothing but 1 plus 0 and 1 minus 0. So, this is going to be 1 1, and T of 0 1 is nothing but 0 plus 1 and x minus y. So, 0 minus 1. So, I am going to have 1 minus 1. Therefore, the transformation on x y is given by x into the transformation, what is that? X into transformation of the vector 1 0 plus y into the transformation on the vector 0 1, which is nothing but x into the transformation of 1 0 is basically this vector. So, x into 1 1, and the transformation of y is basically this vector 1 minus 1. So, I am going to write this as y into 1 minus 1. So, what are we going to do? You clearly see this is going to be 1 1 1 minus 1 into x y. So, what are we going to say? The matrix that captures, so the matrix that captures the transformation T, which is going to map every vector x y to x plus y and x minus y, is going to be this matrix, which is 1 1 1 minus 1, where T maps, T is a map that takes x y to x plus y and x minus y. Now, we have a question. What is the question? Is it always the map, is the map always going to map a vector in R2 to another vector in R2, or can it map a vector in R2 to R3 or R3 to R2 or any Rn to Rm or any Rm to Rn? That is something which we are going to see. So, what we will do is, in the next class we will look at what a transformation, how do we get the matrix representation of the transformation of any vector in, say, in any Rn to any Rm. So, that will be the focus of the next lecture, and we will follow it up with eigenvalues and eigenvectors.
Namaste.